Welcome back to the Art of Electronics. In today's video, I'm going through exercise 1.34. In this exercise, we need to use a phasor diagram to obtain the low-pass filter response, which we previously got in the book. So the previous derivation that the book is referencing is section 1.7.9 and equation 1.36, which you can see on the screen now. This equation showed us that V out is equal to V in multiplied by 1 over the square root of 1 plus omega squared r squared plus c squared, which is the magnitude response of an RC filter. So this is what we will be trying to show in today's video. So first of all, a little bit on low-pass RC filters and phasor diagrams. We have covered both of these topics before, so I won't go through it in much detail. But essentially, a low-pass RC filter is where you have the capacitor in parallel with the load and the resistor in series with the load. So essentially what this is doing is attenuating any high frequencies that the load will see, as the impedance of this capacitor is very low for high frequencies. So essentially you can imagine this as a potential divider with a resistor that varies with frequency. With high frequency you get a very low resistor here, and with low frequency you get a very high resistor here. So with a high resistor, obviously most of your voltage drop will be across the C, and with a very low resistor, obviously most of your voltage drop that comes from here will be across the R, which the VR won't see. So what this circuit essentially does is it protects the load circuit from any high frequency signals that are present on this, be that noise or anything else. Now moving on to the phasor diagram for an RC filter, we basically represent the real part of this filter using the x-axis over here. So this axis is the real axis where we got resistance R, and on the y-axis we put the imaginary components. So if you look at the impedance of a capacitor, you can denote it as this equation here. So you can see it's got an imaginary part on the top over here. So you can write this on this axis over here. So we have XC on here and the R on here. Now using the phasor diagram, we can basically make it easier to calculate the total impedance of this circuit, which is basically the hypotenuse of this right angle triangle. So obviously you've got a right angle here. This is going negative due to this sign over here. And then we've got the real section from the resistor over here. So if you're looking at Pythagoras theorem, the hypotenuse is equal to the square root of r squared plus xc squared. Before, I described this circuit as a potential divider with the resistance over here replaced with the capacitor. We can write the V out equation in the same way. Basically, if you look at the potential divider equation for two resistors, you get the V out is equal to V in multiplied by the bottom resistor divided by the total resistance of the circuit, so R1 plus R2. Obviously, in this case, we're replacing the bottom resistor with the impedance of the capacitor. And as I said before, the hypotenuse is equal to r squared plus xc squared and the square root of that sum. So what I've got over here now is I've replaced the bottom equation with the total impedance that I got from this hypotenuse, which is r squared plus minus j squared, which goes to 1, and omega squared c squared. And on the top, we have the impedance of the capacitor, which is minus j over omega c. So that's just showing the equation again from the last slide that I've replaced the z with. Now, if I take the magnitude of the equation, as there is no real part on the numerator, which is the top part here, that basically becomes 1 instead of minus j. The magnitude of an imaginary number is basically the square root of a squared plus b squared, where b is the imaginary section. Obviously in here we do not have a real section, so the square root of just the imaginary basically cancels out with the square inside it, so you end up with the equation itself. However, the j sign is gone. Now if I multiply the top and bottom by omega c, we basically get rid of the omega c on the top and we add a omega c on the bottom section over here. To take the omega c inside the square root, first of all, what we need to do is square both sides of the equation. So we put a square on here and we put a square on this. So the square on 1 is basically equal to 1, and on the bottom we end up with omega squared c squared, and this square root disappears. So obviously all of that is in brackets. Now if we multiply that out, we get omega squared c squared r squared plus omega squared c squared divided by omega squared c squared, which obviously these two cancel each other out to end up with 1, which we see here. And then we end up with the omega squared c squared r squared, which you see over here. Now if you remember, we've got a square on this side, so we take that to the other side and becomes a square root, or we multiply both sides by square root. So we get the square root of 1, which is 1, and we get the square root of this equation. So that's how you end up with this part here. Now if you remember from equation 1.36 from the art of electronics, this is the same equation that we had, and it's the equation that we needed to show for the question. So this is the solution for this question over here. And this is how you arrive to it using phasor diagrams. So thank you for watching today. And if you have any questions, please let me know in the comment section below. Bye for now.